Okay, this is going to be the lecture over chapter 16. We're going to do the first part of waves, and the following week we will end up doing the second part. All right, so we'll start out here. Got three different types of waves. We have mechanical waves. These are going to be governed by Newton's laws, and they can exist only within a material medium, such as water, air, and rock. Some examples might be water waves, or sound waves, or seismic waves. The second type of wave is going to be an electromagnetic wave, and these waves require no material medium to exist. So light waves from stars can travel through the vacuum of space to reach us, and all electromagnetic waves travel through a vacuum at the speed of light, which is, roughly 3 times 10 to the 8th meters per second. Matter waves. This is going to be the third type of wave. So these waves are associated with electrons, protons, and other fundamental particles, and even atoms and molecules. Because we commonly think of these particles as constituting matter, such waves are called matter waves. So, transverse and longitudinal waves. So a sinusoidal wave is sent along a string, and a typical string element moves up and down continuously as the wave passes. This is the transverse wave. See here, you've got the wave being created, moves this way with a certain velocity. So a sound wave is set up in an air-filled pipe by moving a piston back and forth. Because the oscillations of an element of the air represented by the dot are parallel to the direction in which the wave travels, the wave is considered to be a longitudinal wave. So here we had a wave, it's kind of traveling, the string elements moving up and down, so that is moving perpendicular to the direction of the wave. So this is actually moving in parallel with the wave as it moves this way. So that's considered to be longitudinal. So we have 5 different snapshots, or x versus y, each at a constant time, of a string wave traveling in the positive direction along an x-axis. The amplitude, y sub m, is going to be indicated. A typical wavelength measured from an arbitrary position is also indicated. So we're looking at our displacement. We have the amplitude here. We have the oscillating term. We know what the phase is. And then once we get in a little bit closer here, you can see the angular wave number. You can see the position. You can see the angular frequency, and then you can see the time. So this function is going to describe this particular wave movement. So if you look at a series of snapshots as the wave moves, you can see the peak of the wave moving this way, and you can see the wavelength distance here at a particular x value. And you can see how that particular part of the wave fluctuates up and down if you were to draw this all the way down through here. The y sub m is going to be the amplitude. It's going to be how far this goes away from the x-axis. So the angular wave number, k, is going to be equal to 2 pi divided by the wavelength. The angular frequency is going to be 2 pi divided by the period. The frequency is going to be the reciprocal of the period. And since we've defined the period as 2 pi divided by, or defined the angular frequency as 2 pi divided by the period, here we're going to have the reciprocal of that. So, speed of a traveling wave. So we've got two snapshots of the wave as it's progressing this direction. At time t is equal to 0, and then at time delta t. So as the wave moves to the right at velocity v, the entire curve shifts a distance delta x during delta t. So it's got a velocity, it shifts a certain distance over a certain amount of time. So the velocity, or the wave speed, is going to be defined as omega divided by k, which is again going to be the angular frequency divided by the angular wave number. That's going to end up with a wavelength over the period, or the wavelength times the frequency. So if you put all of that information together, then your displacement is going to be the amplitude times the sine of kx plus omega t. So speed of a wave on a stretched string is set by properties of the string, linear density, not properties of the wave, such as the frequency or the amplitude. So tau is the tension in newtons in the string. That's what you're seeing here. So you're seeing here that mu is going to be equal to m divided by L. That's going to be the mass divided by the length of the linear density. And then you've got the velocity, which is going to be the tension divided by that linear density. And then take the square root of that. That'll be your speed. So when we set up a wave on a stretched string, we're going to provide energy for the motion of that string. And as the wave moves away from us, it transports that energy as both kinetic energy and elastic potential energy. The rate of the energy transmission is going to be defined as the kinetic energy associated with that string element of mass m. So you can look at it as dk divided by dm. It's going to be given by 1/2 u squared, where this is going to be the transverse speed of the oscillating string element. So it's a lot like 1/2 mv squared. It's just here you're talking about infinitesimal amounts of the kinetic energy as well as the mass. The average power, or the average rate at which energy is transmitted by a sinusoidal wave on a stretched string, is given by 1/2 times mu times the velocity times omega squared times the amplitude squared. So the factors mu and v in this equation depend on the material as well as the tension in the string. The factors omega and the amplitude depend on the process that generates the wave. So by applying Newton's second law to the element's motion, we can derive a general differential equation called the wave equation that's going to govern the travel of waves of any type. So a string element, as a sinusoidal transverse wave, travels on a stretched string. Forces F1 and F2 act as the left and the right ends, producing acceleration with a vertical component, a sub y. So you've got the forces acting here along a certain length. You've got a certain delta x here that you're looking at, and this is going to provide an acceleration in this direction. So the force at the element's right end is directed along the tangent to the element's right side. So you can see here the component of force 2x and component of force 2y. The wave equation. So the second derivative Second partial derivative of y with respect to x is going to be equal to 1 over the velocity squared times the second derivative of y with respect to time. This kind of function pops up not only here in general physics, but also later on in quantum mechanics as well. So this is going to be the general differential equation that governs the travels of waves of all types. So here the waves travel along the x-axis and oscillate parallel to the y-axis, move with a certain speed in either the positive x direction or the negative x direction. So the principle of superposition of waves. So let y sub 1 and y sub 2 be the displacements that the string would experience if each wave traveled alone. The displacement of the string when the waves overlap is then the algebraic sum. This summation of displacements along the string means that overlapping waves algebraically add to produce a resultant wave or a net wave, just like they do with vectors. When you add the two vectors together, you get a resultant vector. Same thing here. Overlapping waves do not in any way alter the travel of the other, which is really kind of neat, because if you ever try to produce, let's say you've got a buddy and you guys are holding a string and you each make the string oscillate up and down, those waves approach each other, you get a superposition, and then they continue on. It's to me, it's always seemed like an odd circumstance, but that's what happens. The resultant wave, due to the interference of two sinusoidal transverse waves, is also a sinusoidal transverse wave with an amplitude and an oscillating term. So you get your displacement, you give your magnitude or the amplitude, and then you have your oscillating term. So constructive and destructive interference. So you've got your superposition wave going on here. Being exactly in phase, the waves, if you were to add these two together, the waves produce a large resultant wave. So you've got two waves here, y1 and y2. They're exactly in phase, so you get this huge oscillation going on here. If they are exactly out of phase, where you've got the nodes and not antinodes, but you've got nodes overlapping each other, then you get a straight line, because this movement up here cancels out this movement down here. Boom, that's what you've got. If you have some sort of intermediate result, you're going to get some kind of wave function here. It won't be as big as this, but it won't be a straight line either. So it just kind of depends on how they're interacting with each other, what phase each one is. And what you are seeing here is, this is when they are exactly in phase. In other words, 0 radians or 0 degrees separation between the two phases. Here, you're looking at something that's completely out of phase, 180 degrees out of phase. And then here you're looking at a phase difference of about 2/3 pi. So a phasor is a vector that rotates around its tail, which is pivoted at the origin of the coordinate system. So the magnitude of the vector is equal to the amplitude of the wave that it represents. So you've got the projections of the two phasors. You've got, let's kind of zoom in here. You've got ym1, ym2, and these are going to be the projections of each. So this is just going to be a snapshot of the two phasors for two waves. Wave 2 is going to be delayed by pi radians. And then you've got wave 1 over there. So if you add the two phasors together, you get the projection of the resultant phasor. And so you can see the y component over here. So it acts just like the other phase, other vectors that you've encountered up to this point. So a second phasor, also of angular speed omega, but of magnitude y of n2, and rotating at a constant angle beta from the first phasor, represents a second wave with a phase constant phi. The resultant wave is represented by the vector sum y prime m of the two phasors. Standing waves. The interference of two identical sinusoidal waves moving in opposite directions produce standing waves. So for a string with fixed ends, like what you've got here, standing wave is going to be given with this amplitude, and this is the oscillating term. Kind of see what's going on there with those standing waves. Harmonics. Standing waves on a string can be set up by reflection of traveling waves from the ends of the string. If an end is fixed, it must be the position of a node. It has to come back to zero there in order to be able to oscillate. This limits the frequencies at which the standing waves will occur on a given string. Each possible frequency is considered to be a resonant frequency, and the corresponding standing wave pattern is an oscillation mode. So for a stretched string of length L with fixed ends, which is what you're seeing here, the resonant frequencies are these. So you can see the first harmonic here, in other words, n is equal to 1. Got the second harmonic, n is equal to 2. Third harmonic, n is equal to 3, so on and so forth. Hey, Tracy. How you doing?
Yeah, can you hear me?
Yes, I can hear you.
Okay.
How's it going?
Good. How are you?
I'm doing all right.
Good. I have bowling league, and I know I'm really far behind, so I'm going to try to listen and participate as much as I can. But yeah.
Okay. That's fine. I was actually getting fairly close here to concluding this particular lecture. I was discussing waves. Matter of fact, I just pretty much hit the end here. I'm going to go through all of these here for everybody to look at. So, tell you what, let me go ahead and stop the recording because I was just going through the